All right, what are we talking about today? Today we're talking about the precise definition of limit. So we've been talking about this concept last week, and we just kind of talked about what we think it means. Right? The limit as x approaches a of f of x equals L means as x gets really, really close to a, the f of x is getting really, really close to L. So we would make tables, we look at graphs. We had some theorems that were based on a more rigorous definition of this. But that was kind of the idea. We have the picture in our head of what the limit looks like. There it is. We don't actually know what's happening at A itself, but we know that as we get closer and closer to A on the x-axis, we get closer and closer to L on the y-axis. Okay? But there were a couple instances where, like when we use technology and things like that, we were led astray. Okay, the classic example was it was a video we had. We were looking at this one. This is one of the video examples. We were looking at this, and this did not look like there was any hope at all for this limit to exist. You follow? But in fact it did. It's just we weren't getting in close enough. If we actually got close enough, we could see that the limit actually as x goes to 0 ended up being 0. You follow? So this begs the question, how close is close? Okay? So I like to think of the limit here as being a guarantee. You're telling me, you're guaranteeing me that I can get the function values, the f of x is the y values, as close as I want to L by getting x close enough to A. Does that make sense? Right? So when you make this statement, it's like a guarantee. The f of x will get closer and closer to L as long as the x gets closer and closer to A. Okay? In other words, if you're claiming that the limit as x goes to A of f of x equals L, then you're basically guaranteeing that we can get f of x as close as we want to L by getting x close enough to A. Make sense or not, folks? It's a guarantee, right? If you're telling me that this limit is 5, then that means that those function values they're getting closer and closer to 5. They're not getting closer and closer to 5.1. They're not getting closer and closer to 4.99999. No, they're getting closer and closer to what? 5. Okay. So we have to go back and think about how we measure distances between real numbers. Okay? And the way we do that is absolute value. Okay? So on the real number line, if I have two real numbers, A and B, The absolute value of a minus b is the distance from A to B. You subtract the numbers, and since distance is always positive, you make it positive. Okay? So for example, if I look at the absolute value of 3 minus 5, 3 minus 5 is negative 2, but the absolute value of negative 2 is 2. And sure enough, that measures the distance here between 3 and 5. That's 2 units. You follow? 2 units. That's your distance. If you have things like the absolute value of, say, x minus 3 equals 2, you can solve this kind of equation by thinking about distance. Because what we're asking for is, okay, I want the distance between x and 3 to be 2. So let's put 3 on the number line. And what are the two numbers that are 2 units away from 3? I could go 2 units this way and get what? 5. I could go 2 units this way and get what? 1. And so I can actually just solve this just thinking about distance. If I wanted the absolute value of x minus 3 less than 2, once again, I can think about this in terms of distance. I'm looking for the distance between x and 3 to be less than 2. So I'm going to start at 3. Go over here to 5. Go over here to 1. But if I want that distance to be less than 2, then what's my answer? I want it to be less than 2. So can I actually get to 5? No. Can I actually get to 1? No. But I could be what? Yeah, anywhere between 1 and 5 works. You follow? You follow or not, folks? Okay. Now, when it comes to limits, typically what happens with x values is we don't actually care what's happening at that central x value. You follow? We just care what's happening as you get close to it. So when we see our definitions here, we'll often see this happen with the x's. And how does that change things? Well, I got the 1 and 5, I got the 3 there. All right, so that's 2 units, 2 units. I want the distance to be less than 2, but greater than 0. So being less than 2 means like going up to here, right? But when is the distance 0? Like when would the distance from x to 3 actually equal 0? When x and 3 are actually the same thing, you follow? So we'll be working with inequalities like this, where we're within 2 units of 3, but not actually at 3. So this, when you see this kind of a construction, this means that we're not at x equals 3. We're just within some distance of 3. You follow? So absolute value is what shows up in this precise definition of limit. And as I may have mentioned last week, calculus kind of got its start in the Western world around the 1600s. It kind of came out from Germany and England around the same time because Western society was ready for it. And they had this sort of loose understanding of limit and convergence and all this stuff, and then it got a little squirrely. And then in the 1800s, things got so bad they had to come back and say, okay, we need to be more precise about what the concept of limit is so we can apply it to these other situations. They were trying to solve engineering problems, and they had to do things with trigonometric functions. Even some of the great folks in the history of mathematics were like, this is too weird, just stay away from it. But what needed to happen was in the 1800s, they had to go back and sort of rethink how they described the concept of limit to make it precise. And this is what they came up with. All right, so this is the topic we're talking about today. It involves absolute values. So here are some properties of absolute values that we're going to see in our machinations today. But we're going to focus primarily, our first example here, we're going to look at a limit that we know and see how we can sort of tease the definition out of this. So we know how to compute this limit from last week. X is getting really close to 3. And as x gets really close to 3, 2 times x is getting really close to 6. And if you take something really close to 6 minus 1, that's getting really close to... Wait, did I do this wrong? Yeah, 1. You follow? Okay. So what this says, so once again, thinking back to this guarantee idea, is that we should be able to get the f of x here, the 2x minus 5, as close as we want to the number 1 by getting x close enough to 3. Does everyone agree that's what we're saying with that concept of limit? All right? So how close is close? So think about this, like let's say you're in a lab. All right? Like some of you go off to chemistry lab. Right? Is it today or tomorrow? When's your chemistry? Today. So you're going to go off to chemistry lab. You're going to have to do something in chemistry lab. It's going to have to be within certain tolerances. You follow? So how close do we want the 2x minus 5 to be 1? Well, let's think of a small positive number. Just what's a small positive number? I don't know. Like 0.1 units, okay? So let's do that. Let's say 0.1 units. So let's say we want the 2x minus 5 to be within 0.1 units of 1. Okay? So once again, 2x minus 5, that's some real number. 1 is another real number. And so we can measure the distance from 2x minus 5 minus 1. This is the distance between 2x minus 5 and 1. We want that less than 0.1. Okay? So we want 2x minus 5 to be within 0.1 units of 1. So that's the 2x minus 5 going into there. The tolerance we have here is 0.1. It's going in there. Of what number? The distance, 1. You see where all the pieces parts are getting plugged in. Okay? So then the question is, how close does x need to be to the number 3 to make this happen? Right? So going back, right, we can get 2x minus 5 as close as we want to 1 by getting x close enough to 3. How close do we want 2x minus 5 to be with the 1? 0.1 units. You follow? So we should be able to figure out what values of x is going to make that happen. Right? So we're going to do some algebra now, and then we're going to come back and look what's going on the graph, and then we'll tie them all together. Okay? So let's just start simplifying. Within the absolute value, 2x minus 5 minus 1, that's the same as 2x minus what? 6. Less than 0.1. Okay. Now, I'm trying to figure out how close we have to get to x equals 3. You follow? So if I think about that, what am I looking for here? If I look at the distance from x to 3, that's the absolute value of x minus 3. You follow? So this is what I'm looking for. Can you see how we can get an x minus 3 inside the absolute value here? Yeah, what do I have to do? Got to factor out a 2. Okay. Now the question is, how does the absolute value handle multiplication? All right, we talked about this last week. Constructively, the absolute value just is going to make stuff positive. So if you multiply things together and then make things positive, that's going to be the same as making things positive and then doing what? Multiplying them together. So the product rule says this is the absolute value of 2 times the absolute value of x minus 3. And folks, what's the absolute value of 2? 2. So I can solve for the absolute value of x minus 3. I can figure out how close x has to be by doing what to both sides? Dividing by 2. And what's 0.1 divided by 2? 0.05. Okay. Now, all of this work is reversible. You follow? If I start off with the absolute value of x minus 3 less than 0.05, I could multiply both sides by 2. I could undo the product rule, and I could get back to this. You follow? So this is all reversible. So I could start with this and work backwards. Okay, so how close does x have to be? Answer, 0.05 units. Okay, so let's check it. We can check things graphically. So that's what we'll do. So fire up Desmos here. Gotta do the standard window here. Let's start off with the standard window, 5 to 5. Now, we're looking at the limit as x approaches 3 of f of x. And we're claiming that that is 1. All right? We're giving ourselves, so we're going to go, I'm going to go put in the y equals 1 because that's our limit value. I'll put a little dotted line in there. Okay, that's our limiting value. You follow? And we wanted to get how close to 1? We wanted to be within how much of 1? What was our tolerance there? 0.1. So, okay, so I could, on the high side, I could add 0.1 to that. Or I could subtract 1 from that. You follow? So, if I think about this geometrically, if I want the absolute value of 2x minus 5 minus 1 to be less than 0.1, right? Remember, the 2x minus 5, these are the y values. What I'm trying to do geometrically is I'm trying to trap that line between the two purple horizontal lines. You with me or not? Because that's the only tolerance I have. Okay? And I have to accomplish that by getting close enough to 3. Now, how close to 3 did we say we're going to have to be to make that happen? 0.05. So I'll go ahead and put x equals 3 in there. But once again, I'll put a dotted line in there. So I can go 3 minus 0.5 on the low end. So 0.05. I'll put a dotted line there. That's as big as I think I can go. Okay. So let's zoom in on this window here. Let's go from 2.9 to 3.1. And let's go from 0.8 to 2.2. There it is. Let's square it up a little bit. There. All right, so does this work? For my f of x to be within 0.1 units of 1, I need to trap the line between these two dotted lines. You follow? So here's my target limit here. My L, that didn't go well. My L, my target limit is 1. So this is the line y equals 1. I'm allowing myself .1 units of error. You follow? Up and down. So this top line is the y equals 1.1 line. The bottom line is the y equals 0.9. You follow? Now, in order to trap the line, this is the f of x line. So this is my y equals f of x, 2x minus 5. I need to trap this diagonal line between these two horizontal lines. You follow? All right. The claim is I can do that by getting close enough to 3. So there's the x equals 3. So this was the 3.05. And then this was the 2.95. So based on the algebra, it says I can accomplish that if I let x be within 0.05 units of 3. So do you see how if x is running around here? So if x is between these values, then it's trapping the function between those values. See what's happening? See how it's got boxed in or not, folks? That's the whole concept. Okay? Except maybe within 0.1 units, maybe that's not a strong enough tolerance. Maybe you want to dial this back. You follow? Maybe 0.01, maybe that's not small enough, right? Maybe we want to do this like 0.0001. You follow? Let me ask you this. If I change this to 0.0001, does it affect anything we do on the left-hand side of the equation? No. The only time this number factors into anything is when we get down to what? Here. You with me or not? And then that's just whatever number goes in there, I'm just going to end up cutting it in what? In half. So for example, let's do this graphically. Let's put a couple extra zeros. Let's go 0, 0 in there. Let's go 0, 0 in there. And then, let's see, 0, 0, 0, 0. Okay. Oop. Did it work? You see how the line is trapped between these two things, folks? Okay. And that's the limit. So basically, this is what the formal definition means. So we'll do it for this case, and then we'll generalize. So the limit as x approaches 3 of 2x minus 5 equals 1 means we can get 2x minus 5 within, and so within we need some parameter, some letter that tells us how close I want the y values to be. So we're gonna use the Greek letter epsilon. Epsilon. Epsilon units of 1 by getting x within, and we need some, letter, some variable that tells us how close x has to be. So within this letter, that's the lowercase delta units of 3. Okay, so this is epsilon. It's like the Greek letter for e, so think of this as like our error. So we're letting the function have a certain amount of error. Think of delta as, think of that, that's like the Greek letter for d. Think of that as distance. So epsilons are always the error on the y-axis. Delta is always the distance on the x-axis. So we'll draw a picture here, then we'll annotate the graph. So here's kind of the situation we got going on the graph. This is my target number 1. I can go epsilon above or below that. This is my target x value here, 3. This is my delta there. So epsilon is going to be your error on the y. Delta is going to be your distance on the x. So let me mark this up here. So this distance here, this is our epsilon. That's your distance here on the y-axis. This is your distance here, delta. That's how far left and right you can go. That's your distance on the x-axis. You follow? Epsilon, y's, error in the output, deltas, distance of between the inputs. So delta tells you how close you need to get to the x value to guarantee that the functions are close to the y value. Make sense or not? So now here is the formal definition. In a generic case. So definition. So the limit as x approaches a of f of x equals L means, given epsilon greater than 0. So epsilon, remember, think of that, that's your small error in the outputs, 0.1, 0.01, etc. There is a delta greater than 0. Delta is going to be how close you get to x on the x-axis to make this work. Such that if x is within delta units of a, but not actually at a, okay, so that's what this part means, so we'll annotate it. X is within delta units of a, not actually at a. All right, so that's this part. Then f of x is within epsilon units of L. And that way, no matter what you need for epsilon, no matter how small epsilon you pick, you've been able to come up with a delta that's going to do the job. You follow? So you need to have for every epsilon, you need to have a delta that's going to do the job. All right? So to apply this definition to particular situations, and we'll go back and then close the loop on the one we started with today, you need to write this up with a certain amount of formalism, okay? Because these are like basically mini proofs, all right? So we'll work through one together, and then I have a video with several more of them. And then we'll dive deeper in looking at what can happen. There's other cases that can happen. If you take the what calculus grows up into in like junior level math courses, it's called analysis. So we're sort of doing some prep work for that course. We're not going to go too far into it though. But there's a certain amount of formalism here, okay? So we need to write things up in a particular way. So suppose we want to use the precise definition of limit to actually prove the limit as x approaches 3 of 2x minus 5 equals 1. So we want to prove this limit is 1 using the definition involving the absolute values. Okay? What does it mean to prove something using a definition? It means that we have to show that the stuff in front of us we can get to satisfy the definition. All right? So the way I like to break this down is I like to break this down into two parts. The scratch work part, which is kind of like what we did already, where given an epsilon, we'll figure out what the delta should be, and then the formal write-up. Okay? So this is like in your science classes, right? Sometimes if you take a science class, you have like a formal report. You ever have to do one of these? You get into the lab, you break stuff, things go crazy. You have all your data sheets, right? But then you have to put all that work together and kind of summarize it and formalize it. So that's kind of what we do here. So step 1 in these proofs will always be scratch work. Will always be scratch work. And we're always going to start off with what we want. What we want is the conclusion here of the formal definition. We always want this to happen. That's our goal, right? We want to get the function values close enough to the limit value. So we're going to start off here. From the definition, we want the f of x minus L to be less than epsilon. In this particular case, the f of x is what? 2x minus 5. The L is 1. Okay? That's what we want. And what do we need to find? What we need to find is this delta. It just says, given an epsilon bigger than 0, there is a delta. Where am I supposed to find that delta? That's our job to figure that out. You follow? So if someone walks in, they walk in the classroom, they give us epsilon equals 0.00 or whatever, or epsilon equals like 6 times 10 to the minus 34th. That's like clock length or something. Then we need to have a delta ready for them. You follow? You bring in an epsilon, I need a delta ready so that this happens. Now, you know, this is part of the definition. Most things we work with, we won't need to worry about that part. But so what are we on the lookout for? We need to find this delta. That's what we need to find. You follow? So we need to have this happen. So in this particular case, the A is 3. So we're on the lookout for that x minus 3. You follow? So we're going to basically do the same algebra we did a few minutes ago, but instead of having a 0.1 or a 0.01 or whatever, we're just going to do that same algebra with that epsilon in there. So we're going to start with the 2x minus 6 less than epsilon, just like we had before. We're going to factor that 2 out just like we had before. We're going to use the product rule just like before. And we're going to realize the absolute value of 2 is just 2, just like before. Then we're going to divide both sides by 2, just like before. You see how the algebra we did is the exact same algebra we did just a few minutes ago? Now we just have an epsilon over there. So this is what we're looking for, is the we're looking for this, right? We need this to happen, and guess what? I found that. So x minus 3 less than delta, looks like I find myself a delta. It's what? Epsilon over 2. Which is what we said earlier. Whatever tolerance you gave me, 0.1, we just cut it in half. All right? And can anyone think of why we're cutting it in half all the time? Anything special about this function that would lead you to believe that that would always happen? What kind of thing is that? What kind of graph is that? It's a line, right? What's the slope of that line? The slope is 2. That means that on the line, if you go over, for every 1 unit to go over, you go up how far? 2. You follow? So if I'm restricted to going up epsilon units, then what do I have to do here? If it's a 2-to-1 ratio, then what's this going to have to be all the time? Make sense or not, folks? And pretty much everything you'll be working with is going to be linear. So that's always going to work. Okay, so that's the scratch work. The scratch work is helps us figure out what the delta to be. Now we need the formal write-up. And once again, this is a formality, so it has a particular structure to it. So every formal proof is going to start off with the following. Given epsilon greater than 0, choose, because remember, that's what we need to show. We need to tell them, you walk in with an epsilon, you got to pick this delta. Choose delta to be, and in this case, we're going to choose delta to be epsilon over 2. And then if 0 is less than the absolute value of x minus 3 is less than epsilon over 2, then, so now we're having to prove that our pick for epsilon, or our pick for delta, will work for every epsilon. So I have to algebraically show that if I have x minus 3 with an epsilon over 2 units, so if x is with an epsilon over 2 units of 3, I have to show that I've got the y value stuff going on. So I'm going to start off with 2x minus 3 minus 1 equals, and now I'm going to put in 3 dots. Because I've already done all this algebra. You follow? I'm going to get right down to here. This was the 2x minus 5 minus 1 less than epsilon, all the way down to this part right here. Oop, I lost my proof. Equals 2 absolute value x minus 3. And once again, you can put those dots in there because you got the scratch work that shows it. And then this is where this kicks in. If this is less than epsilon over 2, this will be less than 2 times epsilon over 2, which is epsilon. And I've shown what I needed to show. I've shown that if you pick your delta to be epsilon over 2, then your f of x minus your L will be less than epsilon. Okay? That's the formal proof. You figure out, you start with an epsilon, you get a delta, and then you weave it together in this sort of sentence. All right? So we'll try one more, and then there's a video with more examples. So we're going to try this one because it's got fractions and negatives in it. So I'm looking at the limit as x approaches negative 2 of 4 minus x over 3. Now, we know what this should be. As x gets really close to negative 2, 4 minus x will get really close to what? 6. 6 over 3 is going to be 2. Okay. So that's what that limit should be. Okay? But now we want to use the formal definition. To prove this. So we have two parts. We've got the scratch work, and then we got the formal proof. So the scratch work always starts off with what we want. And what we want is we always want the f of x minus the L to be less than epsilon. They're going to tell us what the epsilon is. We don't know what it is. So we're going to just work with epsilon for now. In this particular case, what's our function? What's our f of x? F of x is? That's the 4 minus x over the 3 minus, what's the target limit L? We're claiming that the f of x's are getting close to 2. Right? And now we need to look at what we need to find. What we need to find is we need the absolute value of x minus a to be less than our delta. That's what our delta is. We need to figure out our delta. So in this particular case, what are we on the lookout for? We want x, we're getting x really close to what number? X is getting close to? Negative 2. Which, you got two negatives. Really what we're looking for is the absolute value of x what? Plus 2. So that's what we're on the lookout for. So our job is to start with what we want and do algebra to see the x plus 2 fall out. You follow? And whatever the x plus 2 is less than, then that's going to be our delta. So here we go. We're going to start off with that. Once again, this is what we want. And we've got to do some algebraic simplification to get the x in there by itself. You follow? So what can we do with these fractions here? I can't just add them together as is. I have to do what? And the common denominator would be? Yeah, 6 over 3. So far, so good? Now I've got the same denominator. I can subtract the numerators. Okay. And in the numerator, let's write that first. I've got a minus x minus 2. So far, so good? All right, now, in every single one of these problems, the x in there always has a coefficient of 1. You with me or not? So every time you go through this, whatever you've got in with your x, you're going to factor out its coefficient. What's the coefficient of x here? It's a negative, but that's really a negative what? So let's factor that out. And what would I be left with then? An x plus 2. Ooh, that's good. I'm looking for that. You follow? I just got to get everything else out of the way now. So once again, we use properties of absolute values. The absolute value works well with multiplication and division. If you think of it constructively, the absolute value, once again, is just going to make stuff positive. If you're multiplying and dividing numbers, you can either make them positive and then multiply and divide them, or vice versa. So we're going to use our properties. And say hi to Dr. Thomas for me. Okay. What's the absolute value of negative 1? X plus 2. What's the absolute value of 3? So there we go. And now to get the x plus 2 by itself, I do what to both sides? Multiply by 3. Boom. That's what I'm looking for. Here I've got my x plus 2, so that is going to be my delta. Does everyone see how we're identifying the delta? Okay. Now, it's really important to write out every single step, because common mistakes, students will factor the negative out and forget that there's an absolute value there. You follow? Your epsilon and your delta should always be positive numbers. If your delta has a negative in it, that means you forgot to take an absolute value of something somewhere. You follow? So write out each step. So this is the scratch work. So let's look at the formal proof. So every formal proof starts off with given epsilon greater than 0, choose delta to be whatever you figured out delta would be. So in this particular case, we've done our scratch work. The delta should be what? 3 epsilon. Okay? So that's the first line of every formal proof is that. And then we have the if-then statement. If 0 is less than the absolute value of x plus 2 is less than delta, or in this case 3 epsilon, then so this was the delta we were supposed to find. So going back to the definition, right? Now we're at this part. We have to show that this will work. We'll have to show that the f of x minus the L is always going to be less than epsilon if this happens. So then, the absolute value of f of x minus L, so in this case the f of x is the 4 minus x over 3 minus 2 equals, and once again, we're going to put in dot, 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 because we've shown this algebra already. We go to our scratch work. All right, we've shown all of this reduces down to right here. So we always, it's the last step, the step before we mess around, because we want things to be less than epsilon when they're done. You follow? So we always jump to the step before we figure out what the delta is. The absolute value of x plus 2 over 3. And then this is where we use the fact that x plus 2 is less than 3 epsilon. So we're going to put this as less than 3 epsilon over 3, which is what? Epsilon. So this shows that if you give me an epsilon, my choice of delta will always get your f of x minus L less than that epsilon. You follow? Now, we can sort of, this is the algebraic proof, this is the algebraic check that that'll work. We can check on Desmos, all right, with specific epsilons and deltas. Any question on the scratch work? We start with what we want, f of x minus L less than epsilon. And then we have to go figure out what that delta is by getting, that's your x. So remember, epsilon is what they're telling us. That's how far they want to nudge on the y. Delta is how much we have, how close we have to get. Okay? It's kind of like if you were, in a movie projector back in the old days, and you have to get the projection within on a certain screen to fill it up. That's like your epsilon stuff. That's where the image is. The delta is the controls at the back that you can fine tune to get it to fit in that window. Follow? So if we wanted to do like a quick check of this, we'd start off with our f of x, which is different. It's what? 4 minus x over 3. The y value, the limit value we care about is 2. The x value we care about is what? X was getting close to, in the limit. X was getting close to what number? -2. All right. So if we pick our epsilon as 0.01, so the epsilon is 0.001, then the delta we said would work would be 3 epsilon, so it'd be 0.003. You follow? So let's go over here. So we'll have negative 2 minus 0.003, negative 2 plus 0.003, and let's adjust our windows so we're near negative 2 and negative 2 and 1. So I guess we want maybe, I don't know, negative 2.005 maybe, then negative 1.995 maybe. Here we go. Let's see. Negative 1.997. No, wait, I got it backwards. That's why. 2.003. Negative 1.997. And the y's. Negative 1.001. 0.999. Oh, I got it negative. There we go. Okay. Now we should be able to see it in here now. One point. Let's try this again. 0.999. 1.001. Where did it go? Oh, it's because it should be this. It should be this. 1.001. I have it too. I'm trying to type these numbers in, and I'm just not being successful at that. There we go. And where's the function at? 4 minus x over 3. Oh, we were trying to get close to 2. All right, that's why. Okay, just a second. So we're up at 2 here. Oh, 2. That's why the function's not there. So we'll go to 1.998, 2.002. There it is. Okay. So there's, you can see the line there. I'll zoom in a little bit, try not to lose it. So it's almost there. But we can see here, these are the extremes on the x, minus 2.003, minus 1.997. So if the x is within this blue band here, then the y is trapped within that the purple lines there. You see you see how it gets trapped into that box? See how it's getting boxed in? Okay. And it's a 3-to-1 ratio because of the slope. Now you could say, well, what if I wanted to be extra cautious? Like, would this work? Does that work? If my x is between these two lines, is the graph trapped between those purple lines? So if I look, so if I look here, so remember what my goal is. My goal is I got to make sure I got to make sure that the graph lives vertically between these two things. You follow? Now, if I pick an x here, the line still lives vertically between those things. You with me or not? It's not beyond those purple lines. So the delta we get is typically the biggest delta when we go through these sorts of machinations. However, if I go more than that, let's say I go 5 here, you see here how the line has escaped? Because if I pick an x anywhere from here to here, you see how the line has escaped over here? It's now below the purple line on this side and above the purple line on that side. You follow or not, folks? Okay. So it got out. So whatever delta we get, that's typically the biggest delta that we need, we could always go smaller. Does that make sense? If you get closer, then you'll just be within a tighter range on the y-axis. All right. Now, as far as, because there's a couple videos I'm going to have you watch where what happens if you have a quadratic function. Well, it gets a little more involved, okay? There's a video on it. That's the type of thing. I think there's like 1 or 2 of them in the book. But that's really, at that point, you're kind of pushing into the junior level type stuff. Example 6 has 4 more examples. These are all lines. On your next take home, you're going to be given one that's going to be a line. So make sure you know how to do this. And at the end here, there is more extra practice with these for you to work on. Okay. Let's look at some graphs to talk about what kind of happens here. Here's a graph. For the scenario below, the limit as x approaches 1 of f of x is 3. So it says estimate a delta so that if 0 is less than the absolute value of x minus delta, or x minus 1 is less than delta, then we have these inequalities. Okay? So these are the types of concepty problems to make sure you're understanding what the algebra is saying and then what you want geometrically to happen. Okay? So once again, remember when you have a statement about the f of x's, this is the statement about the y values. You follow? So this says that you want the y values to be within 1 unit of the target limit 3. You follow? So here's what we do is we go to that graph, and here's the L value here is 3. So here's y equals 3. And we want the f of x minus 3 to be less than 1. So that gives us a distance of how far on the y-axis. We're starting here at 3. How far up and down can I go? 1 unit. So I could be up here, or I could be down here. You follow or not, folks? That's my tolerance. It's asking for the biggest delta to make that work. You follow? So I need to know at what point, and you can kind of see what's going to happen. Delta, I'm going to have to make sure I'm at least here, because that's when the line enters this rectangle, and then no more than where? You follow? See how we're finding those values? We're looking where they intersect. So we're getting close to 1 here. What's the distance from 1? .5. Right? So that would be our delta. Once again, we could go any delta smaller, but it's asking us to estimate the biggest delta. So as long as your x values are in here, if I go up to the graph, the y values are always going to be in there. You see the connection or not, folks? Let's say we want the f of x minus 3 to be less than 0.1. So there's the y equals 3. 0.1 is how far I'm allowed to go up and down on the y-axis. So if I look at the grid here, trying to mark it off. That's 3.5. So 0.1 above would get me to here. 0.1 below would get me to there. You follow? So now I got to trace that back down. Can we estimate a delta? Well, once again, you probably have more control over your, you can use like a sheet of paper to help figure it out. What would you guess your delta to be? Because each of these blocks here are 0.1 units, so what would you pick for your delta? 0.05 maybe? You follow or not, folks? Okay. So this is one of the reasons I like you to be able to print out your stuff, so you can actually, get on there and work it out. Okay. Let's take a look at this one. So for the scenario below, the limit as x goes to 3 of f of x equals 5. Now notice the function itself is what? The function itself is defined at 4. So when x equals 3, the function value is 4. But does the limit care about what's happening actually at x equals 3? No, it just cares what's going on. So this may, as far as we're concerned, that may as well not even be there for what we're doing. You with me or not? Doesn't matter where that is. Okay. So the first one they ask, we want f of x minus 5 to be less than 1. Okay. We'll start there. So let's start off with the 5. So here's the 5. Here's the L equals 5 right here. That's y equals 5. It's less than 1. So I can be as high as 1 or as 1 above or 1 what? Below. So if you take 5 and you add 1 to it, you'd be up at what? 6. Is that going to be an issue for this function at all? No, because this function always lives below 5. You with me or not? Okay, so that's not going to be the issue. The issue is what happens when I go 1 unit below, which is going to be down here at what? Okay, once again, we don't care what's going on at that point at all. We just have to try to get the function trapped. So if you look, what's different about this curve than the other ones we looked at is we have 2 different slopes coming in. You follow? So on the left-hand side, I'm coming down there at 2.5. On the right-hand side, I'm coming down at what? 4. And we're coming into 3. All right, coming into 3. So when we talk about this formal definition of limit, it's a two-sided limit. The delta is a two-sided thing. How far am I allowed to go to the left until I hit the curve? 0.5. How far can I go to the right? 1 whole unit. Which of those two numbers am I going to pick to make sure that on both sides I'm within the tolerance? The 0.5. I got to pick the smaller of the two. Does that make sense? So the delta we're going to pick is the 0.5, and sure enough, if I do that, if I pick any number in here and I go up and look at the graph, my entire graph is going to be trapped in there. You follow? So the delta you pick, it has to work in both directions. So if you get two different deltas, you always want to pick the smaller of the two. Make sense or not? This one here, the limit as x approaches 2 of f of x is 4. So let's look at the f of x minus 4 less than 1. So here's the 4. I can go 1 unit above, 1 unit below. And now I try to figure out my x. So once again, delta is how far, in this case, close to 2 we need to be. We want to pick one that we have to estimate a delta that's going to work. What would you guess for a delta? Like 0.3 or 0.4, something like that? 0.3, 0.4? 0.3-ish, you follow? It's more challenging to do, you follow? And that's because there's a curve to this line. This is actually x squared. It's not a line. Lines are typically easy to handle because it's all slope. And you can see the slope when you zoom in. But this gets a little more involved. And if the geometry gets a little bit more involved, then of course the algebra gets more involved with that kind of limit as well. So just going to walk through this together. It's all written out, but just to kind of show you the wrinkle that happens. If you start with your usual scratch work, you start with your f of x minus L less than epsilon. And you're keeping an eye out. In this case, x is coming into 2. You're looking for the absolute value of x minus 2. You go through, you factor, you get down to here. And here's where things get a little more involved. Because not only do you have your x minus 2, which is what you want, you also have a what? An x plus 2. You follow? Now, if you try to do this, then you get x, the bound on x, depending on what the x is. You follow? You get into this snake eating its own tail kind of a situation. So typically what we do is we say, look, our limit, x is getting close to 2. You follow? So what's close to 2 mean? Well, I don't know. How about we just restrict our attention between 1 and 3? You with me or not? Okay? So what this does is this is, okay, fine. I've got this extra x in here I don't know what to do with. So we're going to just assume that x is between 1 and 3 to start. Because we're getting closer and closer to 2. No one's going to get, oh, look, let's just go between 1 and 3. If that's the case, then this, if x is between 1 and 3, this can't get any bigger than 5. You with me or not? Okay. So now I'll just force this to be less than epsilon. You follow or not, folks? Okay. So when I go to do my delta, once again, well, it's either going to be epsilon over 5 or, well, I restricted things to 1 to 3. Epsilon equals 1, whichever is smaller. So we're either going to have just delta be 1 or epsilon over 5, whichever is smaller. Okay? So when we do that formal proof, I can write this down. So this inequality here, I guess that would be a strict less than. So this is true because x minus 2 is less than delta, which is less than or equal to 1. So that puts it in this interval. So that bounds this piece. And then this is true is because x minus 2 is less than delta, which is less than epsilon over 5. And so that gets this piece. Okay. So that's... So you've got two different deltas. You pick the smaller of the two, and that's how this goes. You can see how complicated this gets. Okay. So there's a video about this one for you to watch. Once again, your focus is going to be on the linear functions. But it's good to see this. And then we've got some discussion of infinite limits. What does it mean for a function to go off to infinity? Well, last week we said that means that it keeps going further and further up the y-axis. You follow? So, how big is big? Given any positive number, you can get close enough to a to get bigger than that. You follow? Let's say we want to get the function values bigger than 50. So here's 50. How close do you have to be to 2 to make that happen? You follow? So when you're going to infinity, it's not that you're trapping the function between two y values, because you can't. You're trying to just show that the function's always above the given y value. So here it looks like, I guess if we're more careful, that's why it's nice to have these printed out. So you can actually go in and do the work on there. What would you guesstimate this to be? So like 0.15 maybe, like somewhere between 0.1 and 0.2. You follow? And you can see the closer we get to 2 here, the further up we get. You follow? Limits at infinity. So you can take that definition. What was this called? This was called a what? So for example, if the horizontal asymptote here is 2, if we really wanted to show the limit was 2, then let's say, we'd have to do like a half. And then where does the x have to be? Well, x is heading off to where, folks? Infinity. So we have to find a place where, for that point on, the function is trapped between those horizontal lines. So x looks like for 2.5. If I want to do a 0.5 epsilon, I'd have to have x bigger than 2. You with me or not? Okay. And so we got a couple of videos that deal with infinite limits, limits at infinity. The point is that this limit definition is robust enough that it can handle all these different little case scenarios that we talked about. Okay? All right. There's some book homework here, just a few from the book, because I really want you to focus on these right here. I got a couple infinite limits and limits at infinity at the end. And then I have everything actually worked out as well. So watch the videos. Those are extra examples. Focus on what's going on the handout here. And then tomorrow we are going to use the limit to define something new. So remember, limits are designed for us to investigate places where algebra fails us. All right? Tomorrow we're going to start what's called the differential calculus. We're going to start talking about derivatives. So we're going to start with a function. We're going to be zooming in on a function. And, you know, most functions that you've experienced, even things that maybe don't look like lines, is sine of x a line? No. It's a what? It's a wave. There it is, right? Certainly not a line. You follow? But look what happens when I pick a point. Let me pick a point on the graph, and let me zoom in on that point. What does it turn into? Looks like a line. Okay? So the sine function, like many functions you've experienced, have a property called local linearity. Okay? And I would like to know what the equation of that line is. Right? For a line, we need a point and a slope. The point's no problem. We can get the point. Algebra tells us the point on the curve, right? Plug the number and get it out. How the heck do we find the slope? That's what we're going to use limits for.